about slope. And one of the reasons I think that I figured out about doing any of this was because we had questions here a couple of weeks ago regarding how somebody would teach something. And I just thought, and this thing came up on some other email of mine, because this is the American Math Society have produced this new blog where you discuss issues of teaching. And this woman who's written this one is Sibylla Beckman, and she's, as you can see there, a distinguished professor at the University of Georgia. And I happen to know her as well because she's the author of one of our textbooks. Some of you may have seen it, you probably have, Gary. She's the author of one of the mathematics for elementary teacher textbooks and that, and so I'm always interested sort of in her ideas, and I just wanted to, I thought this was something sort of to talk about, and so I also see kind of, I mean, the whole idea of slope, I think, is one of the application areas of mathematics, and so I was trying to see how the whole idea of slope connects into applications in other areas, and even we've been looking at possible grants to do with the integration of mathematics and science, and it seems to me that this is a possible avenue for that as well. So I thought that it might be useful to kind of follow what she's talking about, and we can all chime in and talk about it and see what we think about it. You know, so the very first thing there that she's talking about is the basic idea, and we can just look at it. Looking basically the change of an independent variable to a dependent variable, and that it's students, they claim that students have a lot of trouble in understanding the idea of slope. And so this idea of rise over run, but they don't see it as anything other than a set of numbers. So they say mathematics researchers look at the details of how students understand that. So maybe we could take that as a starting point sort of for our discussion about, you know, you've all been teaching slope in various contexts, and do you see students having difficulty learning about slopes? You know, some of you have been tutoring, some of you have been teaching it, and I don't know. I mean, the first time I came across some of this, I presume, is that I just learned equations, and we all learned equations, and we knew what y equals mx was, and we could draw the graph. But it was only then when I was teaching some context of college algebra with applications that I began to try and see, well, what does slope mean, and what does ratio mean, and that, and so, you know, has anyone did you say you're doing some tutoring, Emily, at the moment? Did that come up? Is there the issue of slope and equations of lines? Does that come up much?
Yes, a lot.
What do you see happening there? What are the...
Well, people sometimes have a confusion, like, it's just mostly in the people who are taking like the basic algebra, they get confused with like, in the y equals mx plus b, they might get confused with m is sometimes maybe they just don't remember it, or maybe they forget rise over run, like they get run confused with rise, like they might flip it. And I know even sometimes I flip it, you know, sometimes they get confused, just turn things around. I know that's a way that people just get generally confused, from what I've seen lately.
But is that because they just see these things as just random sort of numbers, the word rise, the word run, and who knows what do they have any idea what it actually means?
They might not know what it means, but I think it also is just because they're not paying attention. Yeah.
Right.
Sometimes I don't pay attention and I get twisted.
Right. Anyone else see any kind of things generally? Have you done some tutoring, Katie? No.
The only thing is I have this is my high school teacher in high school, and it worked really well for all of us. He was a good teacher, and it was just that he didn't spend a really long time on it, and it was one of those like concise, like I feel like with slope you have to be concise with it until they've played with it some, and then you can move on. Yeah. Like you say, and he wouldn't make it to where, because a lot of the rise over run, they know it's up or down or left and right, and he broke it down to where you always are going to go right. Just expand your line until you pick low and go wherever. I mean, he just made it really simple.
Pick low and go, I like that.
Yeah.
I-
Like
I
just
know
pick
what
way,
you're talking about,
pick
yeah.
way low on the x-axis and
Yeah.
then always work right.
They'll have a tendency to pick points right beside each other.
Yeah.
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 But it still is very much, I mean, procedural based, isn't it?
Mm-hmm. It was definitely like a step 1, step 2, and step 3.
I think, and that's kind of like she said, you know, sometimes they just, I've noticed with a lot of people that I tutor anyway, they just they're kind of paying attention, but at the same time, they're like, okay, well, this should be just easy. And for me, you know, I think for a lot of us, it was, you know, pretty easy to understand these concepts. But for those people in, like you said, the college algebra and stuff, they're kind of sitting there like, okay, so I don't really want to put a lot of effort into this because I just have to take this and I just need to pass. And so they kind of sit there and you're like, okay, it's rise over run, and they're like, okay.
But you hit an interesting
I don't
point up there,
understand.
because she said, this person said experienced math teachers know that, you know, that struggle with material that the instructor may seem straightforward, because we, and this is true I think of many concepts we have, we don't remember what it was like to not understand this concept.
Yeah.
You know, there's certain things I don't understand, and I still don't understand them, and it's easy, but things like fractions and slopes, I cannot remember when I didn't get them, so that's why it's always important to try and see what are the struggles people have with it and how they think about it. Gary, when you were doing the college, maybe you're still doing the college algebra with applications, slope would be a very big thing, wouldn't it? I mean,
I would assume so, but I've never done college application.
which one did you do? The business, or you did was it the business the business college algebra? Did you do in college algebra, or was it calculus for business students, or
Well,
what
I've
was
been involved with the business.
that one? Yeah,
It's called intro analysis or something, but it's business math.
but you would
One
be
of them is more algebra than the second one is calculus.
right. But you'd be doing a lot of the conceptual approach to slope there, would you?
Try.
Yeah. What would you have done there?
Well, I mean, I try all kinds of things. Talk about roofing a house and whether or not it's easy to get up on the house and stand up. If it's got a one-to-one, the people who are doing that call it one-to-one, if it's 45-degree angle and what that might mean and what that means. Also talk about climbing the pyramid at Chichen Itza and figure out that those people must have long legs but short feet. And let's see if the kids can figure out what I mean by that. Because in point of fact, that's true. I mean, the little step's only about this big and you can step that high.
Oh, yeah.
You don't have to go very far up if you're afraid of heights until you look around and go, oh my God, you know, how did I get myself?
Yeah.
And so, you know, try to make the point that it has some meaning as to how steep something is
Yeah.
or how.
Right.
But, you know, I can't argue that I have any reason to believe a particularly successful way to approach it.
Right, and I mean, there's other models down here and we'll come to them, but I'm just sort of interested in it because she claims there as well that it seems particularly difficult to teach for some reason. Does slope appear a lot in introductory physics stuff, David?
Definitely.
Yeah.
We teach position, velocity, and acceleration graphs, one over another over another. So you have position versus time, velocity versus time, and acceleration versus time. And then you've got to teach them that the velocity graph, the values on it are the slope of the position graph. And the accelerations are the slope of the velocity graph.
Then you got jerk, right?
Then you got jerk, yeah, that's what I'm there for.
And a lot of that came into play when I was getting some calculus tutoring from not a math person, but an engineer instead, and that's how they explained it to me, and it made a big difference. But I remember like all of a sudden catching on that slope had nothing to do with just rise over run, but rate of change, and that made a big difference for me, but that was a hard one to grasp onto. And I think that's where a lot of the slope like confusion starts, because people just think about plotting points, and then you try and apply it in like a word problem, and they're trying to use it as like a rate of change kind of thing, and then it gets twisted.
Because I found a couple of years ago, it was actually a nice scholar who was a math major and almost about to finish, and they were taking this course 4371 or the equivalent, which is computational techniques for teachers type of thing. And one of the exercises there which really were stumping them was, you know, here's a picture, now draw the slope. But here's a slope, draw the graph. They really had trouble working back from the idea of slope to the graph, because or going from acceleration to slope to the actual position graph. Because the whole idea of that, well, of course you have this arbitrary constant and that sort of thing, but they seem to have a tremendous amount of difficulty in going backwards. It suggested to me that there's something lacking in the actual understanding of it. Yes, here's your formula. I can calculate a derivative, that's the slope. I can calculate another one. Or I can calculate an antiderivative. But to actually look at a graph and say, go backwards from that seemed to be a tremendous challenge. Does slope appear much in chemistry, Amy? Where, what
It
context?
does. Really, it hasn't appeared much until this point in my education, but in analytical chemistry, I'm seeing it a lot when you do statistical analysis. Mostly in like rate of change when you're changing the concentration of a formula or something for that matter. You can graph it and watch as it changes and make sure that you're actually sticking with the compound that you want to stay with based on how the graph changes.
Right, and you're really, that's the next thing that is on here, a kind of a different thing. I mean, here we're just looking at just a graph or a formula there, but she talks then.
It's gotten a lot more complicated than Rise over Run.
Right, you see, that's right, and I mean, she's talking about, where does it go? One of the, I don't know, I'm going up or down here on this, that we might be interested in looking at some other ideas, and she's looking at what she calls here then, let's read that paragraph, what is it about? Proportional representation, pairs of values in a fixed ratio, and pairs of quantities of peach and grape juice. So that's a bit like your solutions now, isn't it?
You know what it is?
Huh?
Yes.
And so, she's looking at it there about what they call a multiple batches view. And it says for every new cup of grape juice, the amount of peach juice increases by 3/2 cups. So you're kind of constantly keeping this fixed ratio between two things. And it says, there's an image then which evokes repeatedly moving to the right and up 3/2. The multiplicative relation is less evident. So that's this idea of multiple batches, she claims, might be a way of explaining stuff a bit more to students, right? From a and I haven't sort of seen that. So basically it says like if you put in a cup of this, you must put in 1.5 cups of the other stuff. And I think that would probably resonate more with chemistry students, and probably less so than with physics students, David. I mean, in the sense that this is either,
Sure.
it's a kind of a chemical mixtures type of approach.
Yeah, you pick your example to match your audience.
Right. But it's funny because I suppose again I think very abstract. Yeah.
Talking about teaching,
Yeah.
okay? You've got two teams, and you're going to increase the number of kids on one team. How fast do you increase the other one? You better increase it 1 by 1. So the slope of horizontal axis, team A, vertical axis, team B, the slope would better be 1. Otherwise, you're going to have a crowd of kids on one team and one on the other.
Right.
Now, that might work with the children,
Right.
elementary kind.
And of course, I always think, that example you have, Gary, about, was it about the free throws? What's that one, like the guy shoots?
Well, it's adding fraction ones where it's correct to add numerators.
Right,
denominator,
that kind of
denominator,
thing.
For what the person's trying to compute, which is his shooting percentage for the game. So he's 1 out of 2 in the first half, he's 2 out of 3 in the second, so he's 3 out of 5 for the game. Right? The question is, but I mean, that's an adding fractions issue.
It
It's
is.
not a slope issue.
Not so much a slope
In the
issue.
business class, one of the things I try to do in business class is make everything, like we said here, in context. So you know what you're making per month. And so you take your profit per month. So at the beginning of the month, the end of the month, you see how much profit you made during that month. That's your profit per month. But then I said, wouldn't the CEO like to have a dial on his wall where he could look at that dial and see what profit he's making per month right at this moment? So we talk about the average. You might figure out what the profit is per month. But the CEO would like to know, at any given point in time, or we on track to have that, and so that's what we have to be into marginal profit.
Right.
Accounting, which is of course the derivative. But, and it's, you know, some kids find that interesting.
Right, because it's there.
So it would be great if you had a speedometer that was reading you dollars per hour that you were making at a given moment in time. And you could increase your speed a little bit, or you could decrease your speed a little bit, or you could do this and the other.
That reminds me now of last week I had a rental car and I was constantly watching the rate because I hadn't paid for the gas. In other words, so I was going to come back with an empty tank, if possible, or as little.
You had paid for the gas.
Yes, that's right. I paid for whatever gas was in it, and then I
You
went.
said hadn't, so
Yeah.
Well.
So what happened, because sometimes you have to come back with a full tank, otherwise they charge you.
Mhm.
But this way you try and get, so I was trying to, I fill my tank in, I don't know, Greeley or someplace, Colorado, and I'm trying to get back somewhere, and I'm watching it going down. But then I start watching, and there isn't, and I thought it would be very interesting to look at the comparison, because you burn gas more if you go too quickly. So if I could drive, I think, 55 to 60 miles an hour, apparently you get optimal gas. So therefore you can kind of watch your tank going down. But then if you start going faster, you watch your tank going down more. So the whole idea of you're looking kind of at the rate of change of gas left in your tank and that, and I got it.
And you want your rental car return to be at the bottom of the hill.
Yeah, you want to kind of.
So then you can coast in and say, here, it's yours.
That's right. I mean, if you could ride back in with no gas, literally, you're perfect. So
You weren't in this country back when they had 55-mile-an-hour speed limits on the interstates, were you?
no, probably not.
Fortunate.
Huh?
You're fortunate.
Maybe it was a good thing.
Think about being out in West Texas, going from, El Paso, and you can only drive 55 miles an hour, for crying out loud.
Well, I mean, it's still almost that way if you're going past El Paso, it's still 55.
Really?
New Mexico.
It is?
Heck, Montana
On
just
the
didn't have
interstate?
speed limits.
Oh, yeah, I'm sorry, not on the interstate.
Not on
no.
the interstate.
Not on
Yeah,
the interstate. Sorry.
Now it's 85.
Yeah,
You go to El Paso, or it's 80
but
or
not on the
85.
interstate.
Of course, that's another example. The whole idea of slope is rate of change.
Mhm.
But I think there's multiple batches ideas. One of the things that she kind of talks that may make things more relevant to that. And there's one other one as well that she talks about. Use what we call it, a variable parts perspective. She said it's often been overlooked. So studying.
Another thing, I don't really think, don't make it.
Huh?
It occurred to me, I make a point of it, but I don't know that I'm making a point of it. Your concept of slope is very much dependent on whether you're in a dynamic situation or a static situation. In the static situation, slope is the steepness of the hill. And you can
Right.
physically look at that. In dynamic situation, it's rate of change. Now, we are so used to interplaying those, we call it the slope of the line, it's just sitting there, rate of change, right? But it's not really, in a static situation,
Well, I mean, it's
it's the
almost,
steepness of the thing, and we're not thinking about, well, I mean, there's a big difference between looking at that steepness of that hill that's
Well,
static
yes.
and looking at your speedometer on your car, which is dynamic.
Right.
Yeah.
because-
Whether that means anything in the way of
Right.
teaching it, I'm not sure, but.
Right, because the slope at that point on the hill never changes. Whereas,
Now, if you're thinking about running your marathon up that hill, now you're in a dynamic situation. But if you're just looking physically at the hill, but
Right,
but for us,
yeah.
it's the same thing, isn't it? And I don't even think about switching back and forth between the rate of change and steepness of the hill.
because
One
under
effect that could be
steepness, I'm
confusing.
still thinking like, it's the rate of change of elevation per like foot laterally.
Yeah, well, that's turning it into, well,
right, but you can turn the two to being the same, can you, Gary, by simply saying like that the slope at any given instant on the hill is sort of the limit, in the same way that where you're, so that when you're talking about the dynamic thing, you're talking about your change of position relative to time, so that a given snapshot in time is as static as a given location on the side of a hill, is it? Could you look at it that way?
no, that's not the way I'm thinking of
Yeah.
it, but, I mean,
I
yeah,
know.
obviously the
Yeah,
same thing. And
right,
for us,
right.
there's no difference. I mean, we just go back and
Right.
forth between these concepts. whether we're thinking of the steepness of something or whether we're thinking of the rate of change of gas flow through a
Right.
pipe or something.
Right.
See, we think of it all the same way, but I'm not sure a kid would. It'd be
Well,
mighty
right,
interesting
that's-
to try to see if there's a difference between,
Right.
if a kid could recognize that steepness is also the same thing that's going on here when we're turning the faucet on and the water flows faster at some time than the other or something.
Right. I think so. I mean, in there.
It's just a different.
A different.
I mean, when I read this thing first, I would just read it because I was sort of interested in what she had to say, and I got kind of tired of it. And it was only then when I started thinking more about it, I went back and started looking at this whole multiple batches. Because certainly to a kid, the whole idea of multiple batches and, you know, mixing grape juice and peach juice seems a totally different thing to climbing a hill. I mean, as you said, it is definitely a dynamic sort of experimental thing.
We look at a graph of a function. You know, the rule of three, graphic and numeric and algebraic.
Right.
And so when I think of a function x squared, I'm thinking of squaring something. When I look at a graph, I'm looking at a physical representation which has the whole thing at one time, which is more of a static kind of picture. And so I'm thinking of derivative as sort of the same thing, rate of change, average rate of change.
Let's see what another model is. She said it's been overlooked by math education research, but we're looking at how future teachers reason with it. For any point on the punchline, see figure 2. So she has. Okay, so the punchline is the mixture. That's the line up the middle, that arrow thing. There are 3 parts for the y coordinate and 2 parts for the x, and all parts are the same size. The parts expand or contract depending on the direction the point moves. The slope is a direct multiplicative comparison between the number of parts of grape and peach juice. Yeah.
See, the teachers, the middle school teachers, they all have a very rigid concept of fraction. A fraction is a slope. That's what we're thinking. Any fraction is a slope.
Right.
Or is a rate of change, or one number over another. They think of this parts the whole and all that stuff, which is
Yeah, right.
which is, they had to take, it took me a while to understand what it was that we were really talking about and the relevance of it to teaching kids fractions.
So this particular thing sort of looks very much like a ratio type of thing, doesn't it? I mean, you basically, and you can do this dynamically. I mean, as you pull that line up and down the middle, both the orange and the green expand in proportion to each other, so you're keeping that fixed ratio thing, you know. So that seems, but that's almost like backing into the equation, isn't it, really, that you're basically saying one coordinate is 3 over 2 times the other one, and it sort of seems fixed enough, definitely.
See, with the teachers, their concept of part and whole, they're really confused then when your units on the numerator are different from your units on the denominator. Because it's, it's confused about what's the whole and what's this is half of the whole and 2/3 of the whole or whatever. And then all of a sudden you have different units in the top and bottom, and then that sort of idea kind of seems to get in the way. Because what does that mean?
Oh yeah, I mean, the whole thing, I have found that with lots of groups in just the whole business of teaching the meaning of fractions, you know, that if you know, what is 1/4 of 2 pizzas, that kind of idea really throws people off. Well, 1/4 is 1/4, but no, 1/4 of 2 pizzas is really a half of a pizza, you know. That whole concept seems to create huge bother.
You can see it in the language too. We treat rates as a special animal. Look at your car, you have miles per hour, and it's expressed as mph, miles per hour, or miles per gallon, mpg. They create an entire separate animal for it, when miles and gallons are things that they already have a concrete understanding for. So our language kind of trips us.
And it makes it hard to break it apart later. I think.
This is why treadmills drive me mad, because apparently, if anyone's interested, I averaged 7 54 per mile, 7 minutes 54 seconds per mile for 5 miles this morning. It didn't feel good because it was hot and humid. But if I was doing that on a treadmill, it wouldn't tell me what my pace per mile was. It would tell me that I was going at 8.2 miles per hour. And that makes me mad, and I'm not very good apparently at doing the conversions because of the language, because we live in this world of like a 6-minute mile is this, a 7-minute mile is this, and this is really about rate of change. But when they switch it to miles per hour, I'm not, because sometimes I'll see, you know, if you're doing something even on a bicycle and you're going quickly and you come into a neighborhood and there's 25 kilometers an hour, and you're kind of wondering, I wonder am I anywhere near that? Because again, my watch, all it'll tell me is I've gone a mile and it took me 6 minutes or something. And so there's a lot of interesting flipping and converting to do those. My thing is that I try to do this while running. Maybe it's why I trip a lot.
I was gonna say,
That's where
probably
chemistry
why you doubled that.
What you say, Katie? Huh?
That's where chemistry comes in handy. They have a lot of really good little conversion techniques through that. Like I remember like high school, the way to set it all up. That's what I have to do is like set it up the way we did in chemistry in high school to get from like these 2 units to something else crazy units. And like crossing things out, yeah.
But I dislike that a lot. In the sense that
A lot of numbers.
because as I said, I have to do this in my head while running. So I really have to start doing conceptual models of, well, if it took me 6 minutes, 39 seconds to do this mile, well, that means it took me 13 minutes and 28 seconds to do 2 miles, and then I'll eventually come up to see how many of these will reach an hour. Well, 13.24 into an hour, and I start doing all this stuff, and apparently that'll be 13, that'll be 6 3/4 or something. So then I'll deduce from all of that I am doing this many miles in an hour. But
I just take my distance at the beginning, my distance in miles at the end, and do the road.
It's dynamic.
Oh yeah, but I need to know different miles, because what
You
about
need to know
the,
while you're running how fast.
well, there's
you're
all
going.
sorts of things. I mean, there's the downhill and there's against the wind. You speaking of slope, I mean, this is an interesting thing. Nobody thinks there's any slope in Lubbock.
Until you're running over it.
But if you run from here, which we often do from sort of the Tech Terrace area to Monterey High School,
You run uphill.
you actually go up. It's only maybe 25 feet, but when you come back down the other side, there is, at the same heart rate, at the same given effort, there's about 20 to 25 seconds per mile of a difference in pace. We've noticed that over and over again. In fact, I said to someone running with me this morning, we should have a marathon here in Lubbock, and we should run it on this course over and over again, and people would overdo it going up. They don't think it's a hill, they'll overdo it, they'll get demoralized, they'll be exhausted. We know there's a 20-second differential, therefore we'll pass them every time coming back. But it is, I mean, you can spend your whole time running looking at these slope things.
That's why I don't run.
Huh?
That's not my reason.
Because then I get to like
That's
distracted
what I do.
and then I'm uncomfortable. So I naturally just like stop running and I'm like thinking about these things. And all of a sudden I'm just like stopping.
But what is
Staring at the floor.
What is this lady proposing? Is she proposing something here?
Well, I think
Somewhere in
she's
the
just
process?
doing, well, we get down to the bottom, but she has a few things we don't think, so we just finished in it what she was looking at. She's looking, her first point is basically, I think that the idea of slope is difficult, and I think we've gone around a bit to realize there are many different ways of looking at it, and it very well can be difficult. And then she says there's many ways to make it, but we suspect that working with multiple batches, etc., should help students develop a more robust understanding, which I think is true, right? In particular, it might help students connect the slope of lines. Some references discuss these. We are currently, she said, conducting detailed studies for students in courses for future teachers reason on these perspectives. Discoveries about how they look at all these things and what is easier will help us to identify productive targets for instruction. And others will try these approaches, the variable parts. So she's basically saying, let's see what mathematics education research is saying about how students are looking at these different ways, and to see if we, and I think she's only in the state of sort of studying it, I did find it kind of interesting that she mentions there about the connection to the whole trigonometric idea. You know, that in a sense, for a fixed angle, this radian measure, sine, cosine, and tangent can be viewed as a fixed number of parts. I didn't kind of... So the radius of a circle is one part of a variable size. So, right. And so the other parts then are based on that. So then the x-coordinate is really is a ratio times r, and the y-coordinate is another ratio times r.
I think
And
the
it-
R is supposed to go in front of the
What?
sine cosine. R is supposed to go in front of the sine cosine.
Oh, I see.
Yeah.
Don't you think, Roger?
Yeah.
But I think she's deliberately written it this way to show that the r is like the y is equal to mx. So the m in this case is
Yeah, okay.
cosine theta. You see, so in other words, and what is cosine theta? It is a slope. It is a rise over a run of some kind, isn't it? So that basically your y coordinate is a slope times your radius.
But I mean, every number is a slope.
Huh?
Every number is a slope.
It is, I suppose you could look at that's true. But I mean, ultimately, sines and cosines are ratios. They're definitively defined as ratios, you know. So
All the
that-
possible ratios you can get.
Right, yeah. And she says, and I think our final point is basically that we need to kind of, you know, look at these things there, where is that? There are useful findings in mathematics education research that could improve mathematics teaching and learning, and she's looking at them. And she's just saying that this particular, she's just grateful for the opportunity to write about this, which is interesting because, I mean, the American Math Society has sort of gone away, I think, a fair bit from looking at the concepts of some, especially the K-12 level of stuff in recent years, and they've started up this math education blog, and the reason I came across all of this thing is because I wrote something about teaching, and they actually put it on here. I don't know where, how do we, is there a back button in this world? Does anyone know what you?
Maybe like go to the very top and sometimes they'll drop down.
Oh,
Well,
okay,
it's
so
like-
Okay, you're already full.
Oh, okay, so now I'm
There
back
you
to,
go.
right. So there are different ones. That's the September one. There is assessment and post-secondary mathematics courses, some thoughts on teaching and learning of mathematical practices, mathematics instruction.
This is a
Oh, that's
cool
been
little
finished.
blog.
Yeah.
It is,
Do you
yeah.
like it? Can you email it to us?
I can, because the role of mathematics department.
Blogs.ams.org.
Gary, you recognize that person?
I can't read it.
It says Diana White, University of Colorado, Denver. That's the person who invited me up to give a nice workshop, which was why I wasn't here last week, because I was giving a nice workshop. Do mathematicians need new journals about education? And being a friendly mathematician.
Ooh, I like that one.
Huh?
Friendly. Sorry.
And being a friendly mathematician. Yeah,
I
I'll send you,
didn't read that.
I'll send out this to people, but as I said, my vested interest is, where's mine?
Can we search for you? We can
I
search.
think, that- is there older ones?
I mean, maybe give
Oh,
it a
sorry.
Yeah, go
older.
up to the upper right, not the X,
You know,
but
if you
the
search
three
there, okay.
lines.
No, there it is.
Oh.
Transformation of a math professor's teaching. So that's why they put me on very soon, because that thing's come back.
Just
Yes.
hover over
Click,
it.
click over somewhere
Click
on
over
the
the gray
page.
area.
Not on that.
No.
Not on
Yes.
that.
Up, like
The background.
Off of
right.
that. Off of
Or
that.
they
There you
just
go,
click,
click.
it just goes away.